Hello everyone, welcome to the fourth lecture of the course Statistical Thermodynamics. The topic of this lecture is a review of classical thermodynamics, specifically the concept of heat. We all have an intuition for heat. We know that when a hot body is in contact with a cold body, heat flows from the hot body to the cold body. We have also learned how to quantify heat in high school. 1 calorie is the heat required to increase the temperature of 1 gram of water by 1 Kelvin. The quantity that distinguishes different substances in terms of how much heat is required to raise its temperature is called specific heat. The amount of heat gained or lost by an object is the product of its mass, specific heat, and change in temperature. We can find the specific heat of any substance by assuming that the total heat is conserved in a heat exchange process. We have to put the object whose specific heat we want to determine in thermal contact with water at a temperature different from itself and measure the temperature of the entire system at thermal equilibrium. Then, by using the equation here, which basically says that heat lost is equal to heat gained, we can find Cs, which is the specific heat of the substance. This sounds quite simple, but there is a potential complication. Heat not only increases temperature, but it can also melt a solid to a liquid or convert a liquid to a gas. That is, heat can bring about a phase change. To appreciate this complication, solve the following calorimetric problem. Suppose 40 grams of ice at minus 20 degrees Celsius and 60 grams of water at 30 degrees Celsius are mixed. What is the temperature and state of the system at equilibrium? You can assume that the heat capacity of ice is half that of water. In my experience, a significant fraction of college seniors stumble over this question, although conceptually it is quite simple. Let us see if you can solve it. Pause the video and try solving this problem now. I will now outline the solution. You can begin by assuming that the final state of the system is liquid water at a temperature greater than 0 degrees Celsius. You can solve for T, and if it comes out to be negative, then your assumption about the final state of the system being a liquid is incorrect. Now, if you assume that the final state of the system is solid ice at a temperature less than 0 degrees Celsius, and on solving T comes out to be positive, then again your assumption is incorrect, and the final state of the system is a mixture of ice and water at 0 degrees Celsius. Your job is then to determine the amount of ice and amount of water which specifies the state of the system. Coming to how heat flows, there are three different mechanisms for this. The first is radiation. This is a way in which heat flows without a medium. It travels via electromagnetic radiation. The second way is convection. In this, the medium translates. Hot fluid rises to the top and cold fluid comes down. The third is conduction. In this way, the heat flows between two regions which are in contact and at different temperatures. Let us now address the question, what is heat? As we have discussed in an earlier lecture, up to about 200 years ago, heat was considered to be a weightless fluid called caloric, which flowed from a hot body to a cold body and was conserved. However, there were a few observations which were puzzling and could not be reconciled with this picture of heat. It was observed that sometimes mechanical energy seemed to disappear. For example, when an object like a bullet hit a wall, pierced it, and stopped, the mechanical energy of the bullet seemed to have disappeared. At the same time, the stationary bullet was found to be really hot. Another observation was that heat could sometimes be produced from nowhere and did not have to flow from a hot body. For example, when we rub our hands, heat seems to be coming from nowhere. These were some hints about heat and mechanical energy being connected, but the question was, is mechanical energy conserved? Joule's experiment in 1843 answered this question. This was his experimental setup. There was a paddle wheel immersed in water which was turned by a falling mass. Suppose the mass, starting at rest, fell by a height h and the final velocity of the mass was v, then he found that mgh was not equal to half mv squared. So some mechanical energy was lost. Interestingly, it was found that for every 4.18 joules of mechanical energy lost, one calorie of heat was added to the water. Joule's statement, very revolutionary for that time, was wherever mechanical force is expended, an exact equivalent of heat is always obtained. But the question remained that how can energy, which is visible and associated with motion, just disappear? Well, it does not really disappear. Today, our understanding is that everything is made up of atoms, and heat is just like the kinetic energy of the atoms. So, heat is fundamentally mechanical energy. Note that overall translation of an object does not count as heat. That is visible motion and counts as kinetic energy of the object. If for a moving object which collides with another and comes to a stop after collision, we keep track of the kinetic energy before and after collision of every single atom in the two objects, then the sum of the kinetic energy before and after collision are exactly the same. The only difference is that before there was a combination of macroscopic and random motion, while after collision there is only random motion. Let us understand the idea of heat being the kinetic energy of atoms quantitatively for a simple system. Let me emphasize that the concept of all matter being made up of atoms is essential to understanding heat, a connection which is not obvious from our intuitive feeling of heat. Let us consider the simplest macroscopic system, which is a dilute gas, that is, an ideal gas. If the gas is heated, we find that its PV increases proportionately with T. We also find that the actual increase in PV is proportional to the amount of the gas. So it seems like for a mass of gas M, PV is proportional to MT. But different gases with the same mass produce different PV, so the proportionality constant depends on the gas. Avogadro in 1811 suggested that PV is proportional to the number of particles of the gas, regardless of what the gas is. So, PV is proportional to NT, where the proportionality does not depend on the gas. The proportionality constant is called the Boltzmann constant and has a value K is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Note that here N is usually a very big number and K is a small number. So this equation is sometimes written more conveniently as PV is equal to nRT, where R is equal to Na times K, where Na is the Avogadro number and N is the number of moles. Now, both N and R are small numbers and easier to work with. Now, let's take a different approach and see if there is a microscopic basis for PV. So, given that a gas is made up of molecules, why is there pressure? Consider a box with gas in it. Say it's a rectangular box of length A, width B, and height C. The pressure inside the box is because the gas particles are moving and bouncing off the walls of the box. The change in momentum produces a pressure. Consider one gas molecule, let's call it molecule 1, which has velocity components u1x, u1y, and u1z along the three orthogonal directions. We will treat the motion along the x direction first and extend the result to other directions. Suppose that the molecule is moving from left to right so that u1x is positive. The x component of momentum px is equal to mu1x. After a perfectly elastic collision from the wall, px is equal to minus mu1x. The change in momentum due to the collision is delta px is equal to 2mu1x. Since the distance between the walls is a, the time between collisions with the right wall is delta t is equal to distance divided by speed is equal to 2a divided by u1x. The force on the right wall is the change in momentum divided by time, that is F1 is equal to delta px divided by delta t is equal to 2mu1x divided by 2a by u1x, that is equal to mu1x squared divided by a. The pressure on the right wall is the force divided by area. So P1 is equal to F1 divided by BC is equal to mu1x squared divided by ABC, which is mu1x squared divided by the volume of the box. The total pressure on the right wall due to all n particles is P is equal to sum over all particles I is 1 to n Pi, which is sum over I m uix squared divided by V. We can take the m by V outside the summation, so we get m by V sum over I uix squared. Now this summation of the squared velocities of all particles can also be written as n times the average of the squared velocity of the particles. So P can be written as m by V multiplied by n multiplied by the average of ux squared. By rearranging, we get PV is equal to Mn average of Ux squared. Let us call this equation 1. We arbitrarily chose the x direction, but we could just as well have chosen the y or z directions. Because the x, y and z directions are equivalent, in other words, the gas is isotropic, we have Ux squared is equal to Uy squared is equal to Uz squared. For any molecule, say molecule I, the total speed Ui squared is equal to Uix squared plus Uiy squared plus Uiz squared. So the average of the square of speed u squared is equal to average of ux squared plus average of uy squared plus average of uz squared. Because no direction is special, ux squared is equal to uy squared is equal to uz squared is equal to 1/3 of u squared. If we substitute this, instead of ux squared average in equation 1, we get PV is equal to 1/3 n m average of u squared. We can see in this equation that a macroscopic property of the gas PV is connected to a molecular property. Experimentally, we had PV is equal to nkt. By comparing the experimental result and the microscopic picture of the gas, we get 1/3 n m average of u squared is equal to nkt. So, m average of u squared is equal to 3kt. Now, putting a factor of 2 in the denominator, we get this. The left-hand side is the average kinetic energy of the molecules, and this equation says that temperature is nothing but a measure of the average kinetic energy of the molecules. Remember that T is in Kelvin. When T is 0, there is no kinetic energy and all motion stops. So, absolute temperature is a measure of molecular agitation. Don't forget that although temperature is a measure of average kinetic energy, the actual thermometer reading of temperature is just a measurable macroscopic property that is exhibited when the thermometer is in contact with the system, like the product of pressure and volume for a gas thermometer. Let us now reconcile our feeling of heat with the microscopic picture of heat. When we hold a hot cup of water in our hand, we are sensing that the kinetic energy of the atoms of the cup are on an average greater than the kinetic energy of the atoms on the surface of our palm. Our hand becomes warm holding the cup because the faster moving particles on the surface of the cup collide with the slower moving particles of our hand and make them move faster. Let us look elaborately at the process of heating water and drinking it from this perspective. When a pot of water is heated on a gas stove, several things are happening. First of all, fuel is burning. This produces fast moving molecules of typically carbon dioxide and water. These bump into atoms and molecules of the air and the bottom of the pot. The atoms of the bottom layer of the pot agitate the atoms in the layers above it. These atoms bump into the water molecules which are in contact with the pot. This sets the molecules of the water in motion till finally they move so fast that the water begins to boil. When we touch a hot kettle or drink the warm water, the fast moving atoms of the kettle or water bump into the slower moving atoms of our skin and increases their kinetic energy. This is signaled by our nervous system as the sensation of heat. Before closing the discussion of heat, let us also understand phase transitions at a microscopic level. In a solid, the atoms have a periodic structure. This is a representation of a one-dimensional solid. The atoms are arranged periodically and the potential energy of the atoms along the length of the solid looks like this. As heat is supplied, the atoms increase their amplitude of vibrational motion till the point that they can go over the potential barrier and move relative to each other. This is what we observe as melting. In a liquid, the atoms and molecules are bound to each other so that there is some structure which is reflected in a radial distribution function. But this does not continue beyond a few shells of molecules, approximately a few angstroms. This is called short range order as opposed to long range order in solids. As the molecules of a liquid keep moving faster, they can overcome the potential energy holding them together that leads to the short range order. This is what we observe as vaporization. In a gas, there is no order at all. We have seen in this lecture how heat leads to an increase in temperature and phase transitions. In the next lecture, we will discuss the first law of thermodynamics. See you for that.